So hello everybody, welcome to this new episode of Robustly Beneficial. Today we're going to discuss a paper from one of my favorite authors of all time, I'd say, Ray Solomonoff. So the particular paper we're going to discuss is called Algorithmic Probability, Its Discovery, Its Properties and Application to Strong AI, which is a paper that Solomonoff wrote in 2009. So late in his career. Actually, he died in 2009, so like very late in his career. And it's a bit of a compilation of all the work, he's like the most important result he's had during his career. And in particular, one thing that is now strongly associated with Solomonoff. In fact, it's called Solomonoff's induction. And to sum it up very quickly, Solomonoff's induction is basically Solomonoff's idea, the result of Solomonoff's idea to combine probability theory and computer science. Like if you mix them together, arguably, if you try to do it yourself, you would likely end up with the same induction as Solomonoff defined. And yeah, Solomonoff essentially claims in this paper and in many of his papers that this is essentially the ultimate solution to the problem of induction. So, yeah, I don't know if one of you want to explain what induction is.
So very basic, maybe definition of induction is so you start from an observation and you want to infer a law, which is the opposite of deduction, where you have a law and then you do a deduction from the law. So a deduction would go like, I know that all cats are mammals. So if I see a cat, I can deduce, I can do the deduction that this cat is a mammal. Induction is the opposite, is that I observe a cat and then I realize that it is a mammal, and then I observe another cat and then I realize it is a mammal. And then I could observe something that is a mammal and not a cat, and then I can observe something that looks like a cat, but it's not a mammal, and then I realize it's not a cat. And the challenge of the scientific method actually is to come up with protocols, we call them algorithms, to go from observations to the law. So how you would allow yourself to induce, to do the induction from your observations to the law.
Yeah. Yeah, and you so Mehdi wrote a paper in Le Monde where he argues, where you argue, that like arguably today at school and in universities, there's perhaps an overemphasis on deduction.
So yeah, it's not a paper in the sense scientific paper. It's just an opinion article, and yeah, in which I discussed the challenges that face the scientific, not the scientific method, but just like the perception, the public perception of the scientific method due to some mismanagement of science and mismanagement of science communication, and maybe some mishandling of pedagogy during the coronavirus crisis. So so the article tackles the one aspect, which is the importance of so not the important, the danger of following intuition. Because so in the beginning of so if you didn't follow the coronavirus crisis, in case you are watching this 1 year later or 5 years later, so in the beginning, some people had a lot of promise, like a lot of hope in one particular molecule, hydroxychloroquine. And based on a paper that used 24 human volunteers, did the induction that this molecule cures the coronavirus, the disease that is due to the virus. And the problem is, like, here we're in a case where it's very hard to do an induction, because the coronavirus, it has a very low lethality, so it kills very little, and so if you observe that people didn't die in your trial and you gave them hydroxychloroquine, you're not really allowed to induce that it's due to hydroxychloroquine, because you could just have gave them water and maybe they would have survived anyway. So for this medical research and various fields of statistics, came up with what we call controlled trials, and we discussed them in extent in another video. And then so the comment is that during this crisis we realized how important it is to teach people about the challenges of induction, especially when you have something with very little probability and it affects a large number. So you can't induce from 24 people, and you have to do control, etc. So there is a big misunderstanding of how induction operates, and my argument in the paper is that so I gave the example with Einstein and several cases where the intuition of Einstein was not exactly what Einstein did when he used the tools of this. Like there's a difference between Einstein plus the algorithms of the scientific method versus Einstein and the intuition of Einstein. So there are like two different things. And Einstein with the tools of the scientific method is arguably more powerful because he's equipped with these algorithms. So that's the paper. But like just to come up here to why it's very important to discuss Solomonoff is that there is a big algorithmic part of induction that can be translated in the following. The goal when we do science is we are trying to outsource the task of our brain to something outside our brain. Like the set of rules of I don't know, algebra is not something we had built in our brain. So it's outsourced, and then we follow them, and then we compute something. It was very easy. I argued like it's very easy to teach people deduction in an outsourced way. So you teach first order logic, and then you do algebra, and then you do mathematical proofs. And many scientific trainings today have a lot of emphasis on deduction. So you learn algebra, you learn chemistry, you learn the laws of chemistry, the laws of biology, and then you go to an exam where you have to do a deduction from the laws you learned to a particular case of the exam. And that's not what we need when we need to know when we need to know a discovery. We need another set of algorithms, another set of rules. And those rules are the rules of induction. And arguably, humanity made a lot of advance in deduction because it's easy compared to induction. And maybe this paper is one of the most important pieces that were written on the algorithmic part of induction.
Yes. I'm just going to read the first paragraph, if you don't mind.
The goose,
because it says essentially what you just said. So yeah, let me read it. My earliest interest in this area arose from my fascination with science and mathematics. However, in first studying geometry, my interest was more in how proofs were discovered than in the theorems themselves. Again, in science, my interest was more in how things were discovered than in the contents of the discoveries. The golden egg was not as exciting as the goose that laid it. Yeah, I love this citation, and I feel like in school, in universities, and in science popularization, science communication, by and large, we insist a lot on the theorems and the discoveries and the theories and what is supposedly known in science. And perhaps arguably we should discuss a lot more about the methods that get us there. And also we should reflect more on this than on the deductive process, because this is a lot trickier and a lot more interesting. How is it that given observations, given like some computations based on examples, for instance, in mathematics, how based on all of this you can go from the data to some inference about the laws that govern the data. Yeah. I feel like there's not enough discussions about this, and along with this, like there's, I think a lot of people just don't know about Solomonoff's theory. From my experience, like most scientists have never heard of Solomonoff, and this is hugely neglected. Like arguably, like this is extremely important. This is like the foundation of knowledge.
I'll just like point. So if you watch the why should the philosophers care about computational complexity? One point we discussed there is the incentives. There are not enough career incentives to care about these aspects of like meta science. So if you are a computer scientist, if you are a physicist, chemist, etc., doing meta science is like taught like is always this like described as something you do when you retire, and then you are like a wise retired physicist. Then you would start thinking about like why physics work and how to make it work better. But during the best part of your career, the most productive part of your career, you should invent new I don't know, chemical protocols for industry, or you should come up with new algorithms in computer science, or you should use more, like you have to find the molecular combinations, which is a very important part of science. But there's not enough incentives to have a large group of people working on epistemology, especially what we call in this podcast and like sort of quantitative forms or algorithmic forms of epistemology.
Yep. Yeah, so I guess now I'll try to explain briefly what Solomonoff's ideas are. So the first feature of Solomonoff's induction is to consider digitized data, empirical data. So this, if it was like he wrote this first in the 1960s, and it may have been very weird back then to imagine that all data can be digitized. And well, that's a leap that he's made, and like he was not the first one to do it. Of course, there was Alan Turing before him, people like Claude Shannon who argued for the digitalization of information and information processing. And he just like agrees with these. He also cites Rudolf Carnap in his paper, like another like computer scientist slash philosopher. Like I think there's a lot of intersection between these two in this kind of a research area. And so now you just assume that whatever you observe, and this is true, like this seems to hold for our senses as well. Like whatever you observe through your eyes, it feels like it can be digitized, like it's like impulses of like electrical impulses typically. And so if you agree that at least digitalization of data is like allows to retain most of the information, or nearly all of the information, or maybe all of the information that your senses are able to collect, then the problem of induction becomes the problem of, now I give you some bits of information, so sequences of zeros and ones, for instance. And the problem is, like, given this long bit string, as we call them, what theories are credible? Like how should you compute the credibility of different theories, and how should you use all of this to make predictions about future bits of information that you will get? And I think just like making this formalization is like one major leap that has been made by Solomonoff.
And the second aspect that I found extremely interesting is that when you said just the word theories, it's not obvious what define a theory and what it is. And I find it very convincing that theories are actually anything that is computable in the sense of Turing computability and Turing completeness. So the way Solomonoff inductions applies this method is given this sequence of data and all the possible algorithms that would generate or would assign probabilities to these sequences of data. Use these algorithms to then make them compute longer to know what they would predict for the future.
Yeah, one thing that's related to this that we already discussed in the previous podcast is, like, we often talk about the laws of nature. Like, arguably here you would want to talk about the laws of the data. What is the law underlying the data? And it's like these days it may seem weird to talk about the law of the data. Like tend to think that the law is written by a human, but historically the law is like very intimately connected to the idea of algorithms, of judgment. Like judgment is the same as algorithm in Arabic, hisab. And it seems that when you're searching for the laws of the data, actually you're searching for an algorithm that's able to, for instance, generate this data.
So just like in case we have a flame war in the comment section when the channel will be famous, So I agree. It's like today we don't use the same, like we say hukm for judgment and hisab for computation.
Yeah.
In our book, we picked the original book of Al-Khwarizmi on algebra, book that gave us the word algorithms. And in that book, Al-Khwarizmi, the guy who gave us the word algebra and algorithm, uses hisab for computation and arguably also for judgment. And some people know that, like in old Arabic, we say the Yom Hisab, which means the day of judgment. So yeah, today there are other words, but originally you could use the same word for both.
Yeah, and just to make it a bit more concrete, like imagine I give you the sequence 1, 2, 4, 8, 16, and I ask you to complete this this sequence, which is like typically like the prime of induction. Then probably you're going to say 32, and probably the reason why you're going to say 32 is that you seem to have discovered some law within the sequence that I gave you, and this law is an algorithm that computes like the powers of 2. And like, this really corresponds to a very simple algorithm that we like all know intuitively very quickly, and that's also very simple. I guess that's another feature of Solomonoff's induction, is that using this language of computation, it allows to naturally and probability as well. It allows to naturally formalize the notion of Occam's razor. So Occam's razor is this saying that has become very widespread in science, and that comes from a guy who was called William Occam, like in the 12th or 13th century, something like this. And he basically said that we should like favor simple theories. And in terms of computer science, there's a very natural formalization of this, which is like a theory is simple if it corresponds to a short algorithm. And the algorithm I just gave with the powers of 2 is very easy to write. Like it's 2 lines of code. Maybe you can even write it in 1 line of code. And that's in virtue of this, of the simplicity in terms of lines of code. It should be credible a priori. And that's the other part that's interesting in Solomonoff induction. So there's this computation part, but there's this other probabilistic part, where what he does is that he basically like just formalizes the idea I've just described. Like he just give higher prior credences to shorter theories. And once you have this, well, essentially you've done. You're done. Like you just look at the predictions made by the different theories. So typically, if it's the power of 2, like the next, the prediction would be 32 in the sequence I gave you. And but there may be other theories that find some other pattern, and by that I mean other algorithms that also generate the sequence 1, 2, 4, 8, 15, 16. And actually, there are algorithms that would complete it, for instance, by 31. It's a very nice video by Figure and Brown about this particular example. And because of this, what Solomonoff proposes is that, well, we look at the prior credences of the 2 theories, then we look at their predictions, and then we say, and our conclusion is going to be an average of all the predictions. So by an average, I don't mean like 31.5 in our case, but I mean a probability distribution that says that with some probability is going to be 31, with another probability is going to be 32. And these probabilities are not going to be half-half. They are going to depend on the prior credence of the 2 different theories, or the power of 2 and the other completion. And this prior credence depends on the simplicity of the 2 theories.
Yeah, and something that Occam's razor, when you simply cite it as given several theories, keep the one that are the shortest description, does not let you directly compute probabilities based on this. But within the formalism of Solomonoff inductions, because each theory is written as an algorithm, you can see exactly the length of the description of the algorithms as a sequence of bits, and that allows you to compute a difference of probabilities between the how much value you assign to each of the theories. And this difference between 2 algorithms would be 1/2 to the power of the differences of their length descriptions, the length of the descriptions.
Yeah. So like well, the length for description of the algorithms, which is very natural concept in computer science. And actually, it has more to do with language theory, which is very strongly connected to computer science. It's like one formalization of computer science, and this naturally gives you Occam's razor. And also, like what I've just described, that in terms like you look at what predicts and you take the average like this. Actually, this has a name. It's called the laws of probability. So this really matches the laws of probability, and you can really interpret them like this. And that's why, in a sense, like Solomonoff is just like the combination of computer science and probability theory. And I bet, like, if you just give it enough time and try to formalize this, you would describe something isomorphic to what Solomonoff did. And this is something that's extremely compelling. Like when I first discovered Solomonoff, like I didn't even read like the nice theorems that we're going to discuss later on. Just looking at the formalization, I was convinced. Like it was so neat and so like you take these two very fundamental theories of knowledge, computer science and probability theory, and like just combine them and you get this. It's like very like the nicest CCP you can imagine if you introduce kind of things. But what's nice about this is that Solomonoff also proves that it works in a very rigorous sense. This is known as the completeness theorem, so Solomonoff's completeness theorem. And what the completeness theorem says is essentially is that if the laws, if the data, if there's any actual law in the data, meaning any algorithm that even partially predicts, like it doesn't need to be a fully predictive theory, but even partially fits the data, generates rather the data. So you can imagine like typically an algorithm with some random seeds, so maybe a randomized algorithm is one possibility. Then Solomonoff's induction is going to quickly essentially identify this pattern. And like what the theorem actually says is more that it's going to make very quickly the same predictions as the one you would make if you knew the true laws of the data. So this is called Solomonoff's completeness theorem, and more precisely, like imagine that at each step, like you receive a new bit of information and you have to predict the next one. So you predict a probability, and you make an error compared to the best possible probability to guess. And this error, like you make an error at each step. And what, so it's like the square of the difference of the probability predictions. And if you add up all of the errors through time to infinity, so you add an infinite amount of errors, well, you actually, if you do this, then you actually get a finite number, which means that like eventually you're going to make mistakes that are so small that eventually they will essentially be equal to 0, and you will essentially make the right predictions. And what's more, like Solomonoff proves that the total number of errors that you make is at most the complexity of the true data distribution, of the true laws of the data. So, and by complexity, again, it's a rigorous notion of complexity. It's what most people know as the Kolmogorov complexity of the true laws, of the algorithms that generate, that describe these true laws. And for the, well, there's an ironic story behind this notion of complexity, because Solomonoff is actually the one who introduced this notion first. And he was not recognized in his time. He eventually was recognized.
In his time,
like not in the 60s, I mean, but like in 2003, he did receive a prize for his discovery of this complexity, of this Kolmogorov complexity, and this prize is called the Kolmogorov Prize. So you get the Kolmogorov Award for inventing the Kolmogorov complexity before Kolmogorov. So as well, like I think it's more fair to call it the the Solomonoff complexity, or maybe the Solomonoff-Kolmogorov complexity.
I think we have now 3 occurrences in academic sources of the Solomonoff complexity. I have the paper on epistemology with the sociologist. So the reviewers didn't know about the Kolmogorov complexity, so they accepted the name Solomonoff complexity. And your book, and the third one, you wrote something else using this. So I think
I don't think I've written something published.
So we call and we advocate so that people start calling it the Solomonoff, the Solomonoff-Kolmogorov complexity, at least.
Yeah, So all in all, I think this should be much better known. Like I think this, like every scientist should learn this at some point. I believe, because it really puts a lot of into perspective what induction is, how hard it is, and what can be done. And also another interesting feature of a result by Solomonoff is the other part of like here I talked about the completeness theorem, but there's also an incompleteness theorem by Solomonoff, which so roughly intuitively it says that if you don't apply Solomonoff's induction, then you're probably going to be incomplete, meaning that for some law of the data, you're going to make an infinite number of errors. Like the sum of all your errors is going to be infinite. You're never going to be able to get it right. So it's actually more subtle than this, because you can always deviate by saying, you can always construct a variant of Solomonoff's induction that just like for the first 10 predictions, for instance, does whatever, and then follows the induction. You can say, well, it's not exactly the same, but the way Solomonoff would prove something is actually by saying that let's consider things that are computable. So one feature I should say about this is that one difficulty of Solomonoff's induction is that though it corresponds to like additions, multiplications, and operations to be done, if you actually want to write down an algorithm that does Solomonoff's induction, then there's going to be one thing that is going to prevent you at some point from writing this algorithm. And this one thing has to do with Turing's halting problem. Essentially, the problem is that you need to list all imaginable theories, all computable theories, and like actually it's all theories that always predict something, that always going to make a predictions about the next bit of information. And actually, the set of all of the algorithms that always predict the next bit of information, well, is the set of algorithms that always terminate. Whenever you give them a beginning of sequence, they always terminate when you ask them to give the next bit. And Turing proved in 1936 that you cannot characterize algorithmically the set of algorithms that always terminate on any input. And so you cannot write a line that says, consider all the theories, like for all the theories T in the list of theories that always terminate. This one line, you cannot write it. And this prevents you from actually turning Solomonoff's induction into an algorithm. And what Solomonoff proved is that actually if you take any algorithm, so Solomonoff's induction is not an algorithm, but if you take any algorithm, then this algorithm will necessarily be incomplete. So you cannot have both computability and completeness. And this is another amazing insight of given by Solomonoff, is that if you want to find out everything about the true laws of the universe, you need, in some sense, to step outside of the realm of what's possible in these laws of the universe. Yeah. So
one quite simple explanation of this would be, if you have an algorithm to do induction, let's call it M. There are some specific environments that would be adversarial to M. So, for example, the environment that computes M and whatever M predicts output the opposite bit of this algorithm would be something that M, by definition, M cannot correctly anticipate, and will make an infinite number of errors over time.
Yeah.
So the answer to that is that if you have composability, as Lee said, then you cannot be complete. And if you want a theory that is complete, then it cannot be computable.
Yeah. Yeah. So this is like the classical diagonalization argument by Cantor, but applied to the Solomonoff setting, and yeah, it's devastating. There are many things that you can do about partially fixing it in some sense, but you're going to, yeah, it's never like completely satisfactory. But yeah, there would be more what you said. That's what I mean. Like it's not the end of the story, but
is there a case of non-devastating diagonal argument?
Yeah, it's always devastating. Yeah. Maybe two other things that are discussed in the paper that are worth mentioning, at least, is that Solomonoff talks a lot about the problem of subjectivity, and I think any Bayesian would. Like, it's very common to associate Bayesianism. Well, there's this objective kind of Bayesianism, but I guess most, well, this is minor, I think, in the set of people who think about Bayesianism. And so usually Bayesianism is strongly tied to at least a lot of subjectivism. Like one of it is just like it's depends on the data. So it's a data-driven epistemology, and this means that if you have different data, then it's going to conclude something else. Arguably, this is a desirable feature of any epistemology. You want to be data-driven, so of course, what you're going to conclude depends on the data you have collected. And given that different agents, different individuals, different algorithms collect different data, well, like any data-driven epistemology will lead them to conclude different things. So that's one kind of subjectivity that seems like very desirable. But a more subtle kind of subjectivity that's more like specific to Bayesianism is that in Bayesianism you have to start with a prior. So you have to start by saying, before looking at any data, what kind of theories are more credible. And Solomonoff tried to remove this by focusing on language, essentially, and by looking at, if you take one language, well, like at least for this language, there's a natural notion of Occam's razor. But then there's a problem of what language are we going to choose. So that's equivalent, like if you read the paper, Solomonoff talks about a machine instead of a language, but that's equivalent. Like any machine defines a language for this machine, so you can talk about a language instead of machines. Anyways, there's a dependence on the language that's fundamentally used by the induction. And Solomonoff says that, so there's this quote, I don't remember if it's from this paper, where he basically says that for a long time he was searching for this for a language that would be absolute, in a sense, that would be universal or that would be objective. And well, at some point he thought he found something, but then he says he realized that there was no utility, no use for this. Like it was okay, you can define this like Turing machine that seems more natural, but yeah, it didn't add more, and it was not that more natural. So, and what Solomonoff suggests is that instead we should fully embrace subjectivity, especially given that subjectivity is not that subjective, it's not that arbitrary, and that has to do with the fact that the Solomonoff complexity, so the how long it is to describe a theory in a given language. So this is important because it affects Occam's razor. But what Solomonoff proved before Kolmogorov, I think, was that this notion of complexity was not extremely dependent on the fundamental language we use, because of this idea of translators. Like any language that's Turing complete, so universal in a sense of Turing, is equivalent to another language, and like in the sense that there exists a way to translate any theory described in one language into the same theory described in another language, and plus the length of the translation of of the translated version is not going to be much longer than for the original version. It's going to be the original version plus a constant that's independent from the theory. And for those who know what I'm talking about, it's the length of the compiler, of the translator. And so this shows that subjectivity, yes, it exists, but it's not going to have that bad of an impact, especially if we have a huge amount of data and for which the right theories are at least millions of bytes long, for instance, because millions of bytes long is going to be much longer than the length of the compiler.
Yes, and the completeness theorem says that if two agents with different subjectivity make predictions after some sufficient time, they will be agreeing on all the predictions they make because they will be using the correct, the true laws of features.
Yeah. So once you've learned enough, like essentially Bayesians agree on predictions if they're exposed to the same data distribution. And then the last thing maybe I want to mention is the idea of diversity. So quite often, like in the way we talk about science, we search for this one true theory. So, for instance, if you listen to physicists, especially those working on the quantum gravity, they'll be using this expression a lot, like the one true law of the universe. And Solomonoff argues against this for the simple reason that his induction actually requires to give a lot of probabilities to a lot of theories. And yes, sometimes there's this one theory that's going to have much larger credences than the others, and it's going to be fine to consider that it is like essentially the one theory you should trust. But what's happening quite often, especially in more complex sciences, is that you're going to have a lot of competing theories that are going to have like good performances, all of them on past data, but that are going to predict different things for the future. What Solomonoff says is that it's very important to take into account all of these theories when making the predictions and to compute the average, in a sense, the probabilistic average, and to reason with uncertainty. Sometimes I talk about a forest of models rather than a tree. Like the whole forest can be useful to make a better prediction. And also it's useful because if one tree of the forest gets cut down because it made a very flawed prediction, well, you have still the rest of the forest to use for future predictions. Yeah. Of course, there will be a lot more I would want to say about Solomonoff, but I think we can leave it here for now. This is already a lot to ponder, and strongly invite each of you to take a look at what Solomonoff has written or what some authors have written about Solomonoff's induction.
So if you are interested, because I know he's very shy to do it, Ray has written a book which is now available in English, The Formula of Knowledge, in which you can learn a lot about...
the equation of knowledge is called.
Sorry, the equation of knowledge, sorry. I really need more coffee. So the equation of knowledge, because in French it's called La Formule du Savoir. And you can learn a lot and maybe more developed about what he just tried to explain in this video.
Yeah.
Maybe we'll put the link of Lay's book
in the description. Good. So thanks for watching, and I hope we'll see you next time.